Hello. In this lecture, we continue discussing how to design a good regression model. And to be more precise, today we concentrate on the issues of autocorrelation and heteroscedasticity. So during this lecture, we will analyze how to indicate autocorrelation and heteroscedasticity. We will analyze possible causes for autocorrelation and heteroscedasticity, and we will discuss how this issue can be handled. So before we proceed, I would like to recall the assumptions to be met if you want to design a good OLS model. Otherwise, the output of your model is not reliable. You cannot use it for drawing any conclusions about the causal links between the variables of interest. So first of all, we assume that values of regressors are independent of error term or residual. Second, we assume zero mean value of disturbance term. As we discussed during one of the first lectures, it's impossible to design such a regression model which would fit all the observations. There will be some residuals and it's totally fine. However, the predicted value of dependent variable can be higher than the value which you observe, which corresponds to the value of independent variable, and it can be lower. So we have positive and negative residuals. And we expect that positive and negative residuals cancel themselves out. So the expected or average value of residual is equal to 0. Third, we assume homoscedasticity or constant variance of the error term. We already discussed this issue and we are going to recall it today. That's why I'm not going to concentrate on it. We assume no autocorrelation of the error term. Analogously, during this lecture, we will discuss autocorrelation in detail. That's why there is no reason to concentrate on it. We assume that number of observations is greater than the numbers of parameters estimated. And this assumption is very easy to meet if you want to design a good regression model. So, as we also discussed, number of degrees of freedom and how easy it is to reject zero hypothesis about zero coefficient actually depends on the size of your sample. So it's always better to have more observations. Then, as I told you, it will be easier to obtain statistically significant variables. So that's why we will not concentrate on this as well. We assume no exact collinearity, and as you remember, exact collinearity or exact linear relationship between two or more variables occurs when two or more variables sum up to some constant value. So you can analyze your variables, like apply your intuition and logic, and you can also run tests for collinearity, as we discussed. That's why we're not going to concentrate on this, and there is no specification bias. Again, we already discussed this issue in detail, and that's why we're not going to concentrate on it in this lecture. Okay. So the question is how to ensure that your estimator is unbiased and efficient. You always start with appropriate model specification. You have to choose proper functional form of your model and you have to choose proper variables. For instance, economic theory tells us that the relationship between capital stock per worker and output per worker can be described using increasing concave function. That's why it would be rather a mistake to assume linear relationship between these variables. Second, you run pre-estimation tests. So you do some prior analysis of your data in order to detect some possible causes for autocorrelation, heteroscedasticity, and exact collinearity. We are going to discuss this test as well. And finally, you conduct post-estimation tests. So post-estimation tests tell you exactly whether there is autocorrelation and heteroscedasticity in your model or there is no such issue. In the next video, we are going to discuss autocorrelation. Like, we're going to recall what autocorrelation is, what might be possible causes, and how to analyze the presence of autocorrelation using post-estimation tests. So yes, see you in the next video, and I hope you enjoyed this one.